The title of my talk simply reflects the result I would like to present. It's short and simple. The three closure of solvable permutation groups is solvable. That's the theorem I would like to prove. I would like to explain at least how to prove this theorem. And this is a joint result of four authors. Eamon O'Brien, Ilya Ponomarenko, Evgeny Vdovin, and me. Well, those who attended previous lecture by Ilya are aware of definition of two closure of permutation group, but let me give you a bit some generalization of this. We start with finite set omega with a permutation group acting on this set G, and fix some positive integer m, and then the action of G, faithful action of G on omega, induces in natural way, just component wisely, the action of G on the m's power of Cartesian power of omega. Well, and the orbits of this induced action are usually called m orbits. And we say that two groups acting on the same set are m equivalent if their m orbits coincide. So it is also easy to understand that if you take two m equivalent group and take a group generated by them, it also be m equivalent to these two groups. So in the set of all all m equivalent subgroups of sim omega, you can take a largest element. So for any group G, for any subgroup G of sim omega, you can take the largest subgroup in sim omega, m equivalent to G, and this is exactly what is the M closure of group G, and this definition belongs to Wieland. He appeared in his lectures delivered in Ohio State University in 1969, and we know it's from the lecture notes of these lectures published in the same year and entitled permutation groups through invariant relation and invariant functions. Well, there is equivalent form of this definition. We can say that M closure is just the set of all permutations of omega, which set-wisely stabilize M orbits of initial group G. And in this sense, it is obvious that the M closure is just the group of the full group of the full automorphism group of some combinatorial structure of, in some sense, which is the structure consisting of omega and relations of arity M, colored relation in this case, but induced with some group action, used by some group action. And this is the reason why the notion of closure of a permutation group is tightly connected with algebraic combinatorics, with some problems like isomorphism of graphs and so on. But in my talk, I prefer to concentrate on the particular result. I say, but not on the connection between between the problem of finding FM closure and other problems we can discuss. Well, let us start from the following observation. If we take M closure, it always contains M+1 closure. It actually can be deduced from the definition. Well, so we have the following decreasing chain of subgroups. One closure includes two closure and so on. And of course, this chain stops at group G. Because, well, if say you set omega is of size n, then certainly M closure of G is equal to n. Even G n minus 1 closure, of course. But so real question here is how far can M closure be from initial group? Well, first of all, let's start with one closure. Since the M closure of M transitive group is certainly the full symmetry group, the one closure in particular of a transitive group is just the full symmetry group. So actually a group and its one closure have in common only one thing, the set of orbits. Well, but the situation changes drastically if we take M greater than 1. Then, as Wieland actually proved, M closure of abelian group is abelian. M closure of P group is P group. M closure of group of order has odd order. And as we know now from the previous talk by Ilya, M closure of nilpotent group is also nilpotent. Well, let me observe here that, of course, in this case, when we take M greater or equal to 2, all this statement is sufficient to prove all the statement just for 2 closures, because 2 closure contains 3 closure and so on and so on. Well, now next class, very important class of groups, of permutation groups, is class of solvable groups. And what can we say? What can we say in this case? First of all, let me observe, it's very easy, that there are 2 transitive solvable groups. Say if you take one-dimensional affine linear group of a field of prime order, so the group of order P times P minus 1, then it of course to transitive. And so its to closure is the whole symmetric group. So if you take P greater or equal to 5, then it's easy to see that we start with a solvable group. Its to closure is not solvable. Well, what we can say here about the case, we can consider further the question what we can say about the M closure of a solvable group when M is greater than 2. What has been known so far? Probably the one result which we can mention here is a result proved by Akademgorodok in 1995. It proved that if we take solvable primitive group, then the 5 closure of this group coincides with the initial group. In fact, the main result of this paper by Serge was following. It's well-known paper actually. He proved that the base number of a solvable primitive group is bounded by 4, and then this corollary. So our result is in some sense corollary of this result, and the observation made by Wieland, if the base number of a group is equal, say, to K, then the group coincides with its K plus 1 closure. Well, by the way, let us call the group which coincides with its M closure M closed. Well, now this is a good point to formulate the main result. So what we prove? We prove that if M is greater than 2, then M closure of any solvable groups is again solvable. And well, at the rest of the talk, I will try to explain how one can prove such result. But we will start with some basic facts on M closures, and further GH is 2 groups acting, permutation group acting on the set omega. And first of all, let me say that the M closure is indeed the closure operator. Well, indeed. M closure contains initial group, initial object. M closure is M closed, and M closure preserves inclusion. Well, this is the first one, the first basic facts, and the second one is it was also observed by Wieland and consists of the following. If we take M greater than or equal to 2, then group G will be M closed, will coincide with its M closure if you can find if there is a point alpha of omega such that the point stabilizer G alpha is M minus 1. Well, let me emphasize here that I'm not. It is not required here that the group G is transitive. It's sufficient to find exactly one point, just one point. Well, now let us, for convenience, say that permutation group is partly regular if it has a faithful regular orbit. Well, and the proposition 1 here, which is a consequence, easy consequence of these basic facts, sounds like that. If M is greater than 1, and M minus 1 point stabilizer of G is partly regular, then the whole group is M plus 1 closed. Well, the proof is really easy, but let us do it. Let us prove this. Well, if G has a partly regular M minus 1 point stabilizer, then of course it has a M point stabilizer which is trivial. And hence, by the previous statement from our slide, it follows that the whole group must be M plus 1 closed. Well, two observations here. First, maybe you can see here that proposition 1, I paint proposition 1 in red. Well, this why is so? Because this statement, alongside with 2 other during my talk, will be used at the very end of the proof, and so I would like to emphasize this at this point. Well, and the second observation is that how I would like to say how this proposition. Let us see how this proposition sounds when M is equal to 2, exactly to 2. Then it sounds like this: if one point stabilizer of G has a faithful regular orbit, then the whole group is tree closed. Well, now we are ready to discuss our theorem. Again, I recall that the 3 closure of a group G includes M closure for every M greater than 3. So it suffices to prove that 3 closure is solvable of our theorem, and this is exactly the fact that we are going to discuss. Okay. So assume that our conclusion is wrong, and G is a minimal counterexample. So that is a counterexample with the least possible degree. Well, my first claim is that such a counterexample must be transitive. Well, the reason why so is the following lemma, well known probably, and at least I don't know the place where the written proof of this lemma. It's just a folklore. So it sounds like this. Let K be let K be permutation group acting on set gamma. L symmetry group, L permutation group acting on the set delta, and the direct product of K and L acts naturally on the disjoint union of gamma and delta. Then M closure of direct product of K and L must be a subgroup is included, is contained in the direct product of M closures of K and L for every M, for every positive integer actually. Well, this is not hard to prove. Well, why our claim follows from this lemma? Let us think a bit about this. Well, if G is not transitive, then there are two proper subset, two proper gamma G invariant subset gamma and delta, in which disjoint union is omega. And G is a subdirect product of its projections on gamma and delta, which we can denote by K and L. And so group G is a subgroup of direct product of K and L. And as we know, this yields that the M closure of G is also the subgroup inside the M closure of the direct product. So M closure of G lies inside this group. And so by lemma it lies inside these groups, but K and L are groups of lesser degree than G. So by induction, they must be solvable. And so G is also solvable. That's all. That's very simple reduction here. Before we go further, let me observe that here, of course, in this lemma, we can change, we can replace the inequality to equality, actually. Well, we don't need it in our proof, so I'm not going to discuss this, but let me at least observe this fact. And also, it is important, where I would like to emphasize that, of course, there are two possible natural action of direct product of permutation groups K and L. First, when K is the direct product acts on the disjoint union, and second one, when this direct product acts on the direct product of the set gamma and delta. Well, and my point is that the same equality like this holds true even if we consider such an action of direct product. Okay, let's go. So my second claim is that G must be, the counterexample must be primitive, and it is based on the following lemma, which was here I have a reference, but very old, and on Russian paper published only in Russian in so-called Latvian Mathematical Journal in 1976. It is a paper by Lev Arkadьевич Kaluzhnin and Misha Klin. What they proved? They proved is that if we take two groups, K and L, K acting on gamma, L acting on delta, and consider the so-called imprimitive action of rest product of K and L. So K and L here acts on the disjoint union of gammas indexed by elements of delta. Then again, M closure of this rest product is just equal to the rest product of again in primitive, of course, rest product of M closures of K and L for every M, but here greater, of course, than 2. Well, if we have such a lemma, we can easily prove that G must be primitive, just by in the same way as we did it in the previous, when we proved previous claim about transitivity of G. Here I'm interested in the question: can we say the same when rest product acts in product action? Because No, the rest product also of groups of permutation group K and L has two natural actions. First, in primitive, and the second, when the imperative action is the action on disjoint union of gammas indexed by delta, and the second action is a so-called product action when the rest product acts on the on Cartesian product of gammas indexed by element from delta. Well, so our question is, does the same hold for the case when we have the second action of the rest product? Well, in m equal to 2, the answer, a general answer is no, as the following example shows. Indeed, if you take the rest product of sim4 and L3 in product action, then it's too close, it's easy to check, is just the rest product of sim4 and sim3. But the group alternating group of degree 3 is regular, so it's of course too close. So the right hand part of this equality is just is equal to this the rest product of symmetric 4 and alternating group of degree 3, and that's all. Well, can we say something, at least something in this case? Yes, we can. And in his paper about the closures of groups of odd order, Sergei Evdokimov and Ilya Ponomarenko 20 years ago proved that if we suppose that K is not the full symmetry group, acting on gamma, then at least the inequality required inequality holds. Well, but what if? But we need to consider the same action of rest product in the case when m is greater than 2. And the good news that in this case we can prove what we need. And my third claim is that group G doesn't, my counterexample of a least possible degree, doesn't reserve any product decomposition of omega, or which in terms of Peter Cameron's book means that G is Daisy group. And it follows from the lemma 3, which says that if we take a tree closure of, if we take a rest product of groups K and L acting in product action, but here we need we need additional maybe strong but natural condition that this rest product is primitive group, because it's not necessarily if rest product acts on the product action, it is not necessarily primitive group. But if we need to assume this in our lemma. But if this is so, then the required inequality holds, and so it's easy to prove claim 3 using lemma 3. Well, let us discuss what means that the group, the rest product of K and L in product action is primitive. It is well known that that this rest product is primitive if and only if the group K is primitive but not regular. So in particular, the size of gamma is at least 3. And L is transitive and non-trivial, so the size of the delta is at least 2. In fact, we proved in our paper a stronger result, and I think that this result is interesting in its own ground. I mean, it has non-trivial proof, and well, I think it will be useful in the further research of closures. And this is the result. Sounds like let me formulate the complete version of this result. So we again start with the groups K and L. consider the rest product in product action. Suppose that this action is primitive, but if we can prove the statement for arbitrary m greater or equal to 2, 3, then we also need to suppose that the size of gamma is at least is greater or equal to m, and the same is true for delta, except the one case when the size of delta is equal to 3, and then we get we can prove we were able to prove this inequality, this inclusion. Maybe it's better to say it like this. And well, it's easy to see that if we take m exactly equal to 3, then these additional conditions disappear. And so lemma 3 is just the direct consequence of proposition 2 and the criterion of primitivity of the rest product and the product action. Well, so let us go further. So now we have a primitive group. Let's forget for a while that it's also basic. For me now it's sufficient that G is just a primitive group, but it also solvable groups. It yields that G is just a affine group. We can identify in natural way the set of points with a vector space, which size over the field of prime order P of dimension D and so on. Well, and consider the, of course, the group is transitive, so all point stabilizers are conjugated, and we can take one of them, which is a stabilizer of the point which identified with 0 vectors in our vector space. And then H, we can consider H as a linear group, as a subgroup in GLDP. And since G is primitive, this group H must be reduced. That's well-known facts. Well, and in this terminology, I would like to formulate next claim. I say that my counterexample is neither subgroup of one-dimensional affine semilinear group, which always which is a maximal subgroup in the group AGLDP, and also G cannot be two transits. Why so? First of all, it is known. Well, you can find it, say, in the PhD dissertation by Zhang Hu, and in the consequent paper published with maybe it was the dissertation was published in, sorry, just a minute. Okay, the paper well all these results were published is by Hu and his supervisors, Michael Giudici, Kai Lee, and Sheryl Prager. Well, and you can take from this that a group gamma L, one-dimensional group of linear semilinear transformation is too closed. And as we know, if the point stabilizer is too close, then the whole group is 3 closed, and that's all. And if G is two transitive group, then we can it is also solvable, so we can apply it to Hubert classifications, and it states that if G is not a subgroup of one-dimensional semilinear group, then there are only finitely many, actually 6 possible sizes for the set omega, and we can easily check that in these cases, the 3 closure of G is also, and we did it, also solvable. Well, let me also introduce his one of the key lemma of our proof, lemma 4. It's also the statement in red. This is the second statement in red. Well, and this lemma states that if you take primitive solvable group, then it will be 3 closed if you can find a non-zero vector alpha such that the restriction of H to the orbit containing alpha is too close. Well, let us go further. Well, now we apply that G is basic, that G doesn't preserve any product decomposition on omega. Well, let me recall that irreducible linear group is imprimitive as a linear group. If the space V contains a proper subspace that's such that V is a direct product of images of this proper subspace under the action of H and primitive otherwise. Well, now, if G, since we know that G is basic, we can claim that H must be primitive as a linear group. Because if not, then G is isomorphic to a subgroup of primitive rest product of two solvable permutation groups of degrees, again, smaller than the degree of G, and be done by lemma 3. Well, third statement in red, lemma 5. Now G is a primitive group, but also we suppose that H is a primitive, this point stabilizer is a primitive as a linear group, so G is a basic one. And under this condition, G will be 3 closed if we can find a non-zero vector alpha such that the size of the stabilizer H alpha is bounded, strictly bounded by the following number. This is actually interesting lemma, and it based on two important and two non-trivial actually facts. First one is the upper bound on the fixity of the group H. Obtained this upper bound was obtained in the paper by Surish, which I mentioned in the previous in my talk previously. Well, I'm not going to explain what fixity means, but nevertheless, it's non-trivial fact. And here we actually need that H is imprimitive as a linear group. And the second fact was it's actually the result on coherent configuration. It gives some sufficient condition for coherent configuration to be partly regular in terms of maximal valency of the coherent configuration and so-called indistinguishing number. This criterion is recent. It was proved in the paper by 4 authors. 2 of them are from China. It's Gang Chen and Zhou Wei here. And 2 authors are from Russia. It's Ilya Ponomarenko and me. Well, this and we use this pure combinatorial actually criterion to prove to prove the lemma you can see on the screen, lemma 5. Well, can go further now. Okay, so now we have group G, which is primitive, and the point stabilizer is a linear group, which is primitive as a linear group. And we also can suppose that this solvable primitive linear group is a maximal, because as we know, the M closure operator preserves the inclusion. So if we prove that two closures, say, if we prove that the theorem for situation when H is the maximal solvable subgroup, we prove the whole thing. We will do the whole thing, and so we can use Supernenko theory of solvable primitive groups, and the following theorem we take it from the paper, the same paper by Akash, which is because it's very clear formulation what was actually done by Dmitry Alexeyevich Supernenko and his prominent monograph, Matrix Groups, published in Russian in 1972 and translated in English 4 years later. Well, what we have? So let H is let H be a maximal solvable primitive linear group. Then it has a normal series which has 4 factors. First factor actually a cyclic group is a multiplicative group of the field of order P to the A. The second factor actually is the direct product of elementary abelian groups, but these elementary abelian groups are images actually of corresponding extra special groups. The order of this factor is the square of the positive integer e, which is divisor of the order of this the cyclic group U. Well, the third factor is a product. But let me say, no, it's a completely reducible subgroup of the product of the symplectic group, which arises as a normalizers of corresponding extra special groups. Well, and the degree and size of the field in these symplectic groups are determined by the factorization of the number E. And well, the last factor is just a cyclic group, and it is actually the image of field automorphism, where was the field from the step 1. Well, let us refer to the integers P, D, A, and E as the parameters of a group H, and so of the group G, the whole group. Well, my fifth claim is that there are only finitely many, actually, in fact, 102 possible sets of parameters of G. How we can prove this? First of all, if group H is partly regular, if it has a faithful regular orbit, then G is 3 closed by proposition 1. Indeed, H is a one point stabilizer, and we apply this proposition and get that G is 3. And so it's solvable. The 3 closure coincides with G, and so it's solvable. That's okay. So we can suppose that H is not partly regular. The study of group, the study of the question when solvable primitive group, primitive linear group has a regular orbit, has a long story, but shortly, about 10 years ago, Yang published a paper when they proved that there are only finitely possibilities for E. Well, then he, maybe 5 years ago, he put in at the archive, the paper where they prove, let's just say in this way, that there are only finitely many possibilities for the set of parameters of in this if group is not partly regular, if H is not partly regular. But when we, about a year ago, when we tried to understand the proof, we discovered that this draft, of course, in archive has a lot of gaps, and Evgeny Vdovin wrote a letter to Yan, and they discussed and things, and decided to complete this task together. Also, Evgeny Vdovin invited his PhD student, Alexey Vasil'ev. Well, this Vasil'ev is not me, it's important. It's Alexey Vasil'ev, is a young guy. And they three proved very recently, it's not submitted yet, that actually if H is not partly regular, then there are only finitely many sets of parameters, and all these parameters are known. And by the way, the largest possible field is of order 73, and the last possible dimension is 636, I suppose. Well, something like that. So there are still a large group there. So in order to complete the proof of the main theorem, one need to check that in all these 102 possible 100 in all cases when group G has one of this possible set of parameters, we need to check that G is still 3 closed. And it was done by means of computer computations. And let me very shortly explain how it was, how we did it. First of all, let me say here that this part of the paper is not just a computation, it's not trivial. It was a very important part of the work, and it actually deserves the probably separate talk. So I'm just briefly and in theoretical manner try to explain what we really did. So for each choice of the parameters, we have computed a full set of pairwise non-conjugated maximal solvable irreducible primitive groups. Of course, we can suppose that we can take only the groups which are not transitive on the non-zero vectors, because we exclude two transitive groups before. And now for each group from this list, from this set, we found a non-zero vector alpha such that the one of the following condition is satisfied. Well, either the orbit of H consisting the element alpha is regular, and then group H is party regular, and the whole group is 3 closed by proposition 1. I hope that you still remember this. The second case, the restriction of H to the orbit, to corresponding orbit, is too close, and then we are done by lemma 4. Or the inequality, the bound, or the size of stabilizer H alpha is bounded by the following number, and we can apply lemma 5. In all the case, we get that the group G must be 3 closed. Well, talking about the computational tools we used was, so let me say, small cases. We used well-known packages iRedsol, and also we use, of course, the package COCO2 to find closures. And for some large cases, but it was the problem that some large cases are not possible to treat just by Iritsol, because the library of Iritsol too small for these cases. And so we will need we use some additional computations in Magma and so on and so on and so on. I'm not going to explain it in more details. But nevertheless, all this work was done, and so we exclude all this or prove that G is not our counterexample cannot have these possible parameters, and so we prove the theorem. And that's all. Thank you very much. That's all. See.
Okay, thank you very much, Andrey, for the nice talk. And are there any questions to the speaker? Okay, I'm sure that yeah, we have some questions, but we need to fix these ideas. And well, actually, I like all proportion and lemmas in red in your talk, but my favorite one is lemma 5, which gives us the size of stabilizer. So it is upper bound, which you use in your computational results. So I just wonder, could you please give us some idea about the combinatorial criteria which was used to get this upper bound?
Well, the problem is that I can't write easily. But the idea is as follows: if you know what is indistinguishable number of coherent configuration, we prove that if H is not if we prove that is a coherent configuration actually is not Paty regular, then the degree of n, the degree of our coherent configuration, sorry, just a moment, should be I would like to find the exact formula. Yes.
Yeah, okay.
We can say, so if a group is not partly regular, then the degree of n should be, the degree of this coherent configuration should be greater or equal to the product of so-called indistinguishable number and the number 2k-1, where k is the maximal valency of the coherent configuration. And you can reformulate actually this in the language in permutation group language. But the problem is that you can prove the corresponding formula just by means of permutation groups. We tried to do so and failed. We realized that we actually need the combinatorial formula to prove what we need about the permutation groups. That's interesting case, interesting situation. We spent a lot of time, let's say, discussing this thing. It was really a tricky part of the job.
Yeah, I see. Yeah. Yeah, it looks so, yeah. It looks so, yeah. Okay, thank you very much, Andrey. And are there any other questions? So since you have this slide to show us, I mean, this computational part, so which part was actually more difficult? So
what do you mean?
Well, what I mean, so you said that you use two packages, GAP and Magma, and when you deal with GAP, then you use small dimension, right? Yeah, but for some large cases, you're right. Large cases means that, what does this mean?
It means that we have you have a lot of groups. Yes, you
Right. Yeah.
And sometimes sizes of the group is too large to
I
use.
see.
There is no you can't use library of.
I see. Okay. I see.
So you need to generate some such groups by hands, or but by hands I mean you need to find the generators of groups from each. It was done by means of Magma. And
I see. Okay, thank you. Are there any other questions?
I have one question.
Yeah, please, Gareth. Yeah.
Early on, you gave us some examples of solvable groups that are not, whose two closures are not solvable, namely doubly transitive groups.
Yes.
Into the obvious examples.
Yes.
Two closure is the whole symmetric group. Can anything be said about simply transitive solvable groups whose two closures are not solvable? Are there simple examples?
There are interesting example. Actually, there is a paper by my PhD student Savelis Krisanov where he gave an examples when the two closure of a solvable group is unsolvable and the composition factor is a group of Lie type. Moreover, there are if you assume only that group G is primitive, not necessarily basic, then there are infinitely many such examples. But the real question is if we restrict ourselves only to basic groups, to groups when the point stabilizer is primitive as a linear group, can we prove in this case that the number of such counterexamples, such examples when the closure of the solvable group two closure is not too solvable? Is there other infinitely many examples of finitely many? My conjecture is that there are only finitely many examples. And maybe next talk will be by Savelis Krisanov, and I hope that he explained at least in the case of groups of rank 3 why there are only finitely many such things.
Okay, thanks.
Okay. Okay, thank you. Are there any other questions to Andrey? Comments? Not at all. Let us thank Andrey again for such an interesting talks with so many interesting new results. Thank you.